Welcome to Curium. As part of Tool 1, you are expected to be able to apply the experimental technique of calorimetry and use it to determine the enthalpy change which is associated with a reaction. Note that the concept of enthalpy change and reactions can be assessed in paper 1A and paper 2 also, but the experimental perspective is most likely to be assessed in paper 1B. There are some key concepts that will be helpful for you to understand before we begin. What is an exothermic reaction? What is specific heat capacity? What is delta H? The formula Q is equal to MC delta T, and we know that this formula is given to you in the data booklet. And the formula delta H is equal to minus Q over N, and note that this formula is not given to you in the data booklet. Let's develop our understanding of calorimetry. It's simply just any technique that you use in order to measure the enthalpy change which is associated with a particular reaction. There are two main types of calorimetry that we focus on in chemistry. There's direct calorimetry, wherein the temperature change of the surroundings can be measured directly. And that's because the reaction that you're measuring happens in solution, and we can measure the temperature change of the solution. There's also indirect calorimetry, and this is what you would do when the temperature change of the surroundings can't be measured directly. In this video, we will only focus on direct calorimetry, and a separate video will focus on indirect calorimetry. Because the focus of calorimetry is measuring the temperature change associated with the reaction, the focus is on making sure that the setup ensures the accuracy of that temperature change. So your reaction will happen in a solvent, it's often water. This is the thing that we will measure the temperature of using a thermometer. We want to make sure that all of the heat that's released by the reaction stays in the solvent so that the temperature change we measure is accurate. So we want to minimize the heat loss to the surroundings. We do this by adding a polystyrene lid to the setup, and also, rather than carrying out the reaction in a beaker, we'll carry it out in a polystyrene cup. So both the lid and the cup are made of polystyrene. This is because polystyrene is an excellent insulator. It has a very low specific heat capacity. That means that all of the heat energy that's produced by the reaction should stay in the solvent. An example of this experiment is when zinc powder is added to a copper sulfate solution. And what's formed is zinc sulfate and copper. So you start with the copper sulfate solution and you add in a spatula of zinc powder. You pop on the lid and then you measure the temperature change. Let's look at an example of the data that you get from this experiment. At the beginning, in your polystyrene cup, all you have is the copper sulfate solution, and that means that the temperature of this solution is going to be quite constant. Once you add the zinc powder, you'll see that the temperature will start to increase. It will reach a maximum temperature that you will record experimentally, and then you will see that the temperature will start to decrease. Why does the temperature start to decrease? This is probably because the reaction has now gone to completion and no more heat is being produced. This means more heat is being lost than is being produced by the reaction. Hence, we get a temperature decrease. One of the things that we can assume here is that the rate of the heat loss is constant. And if we extrapolate that line backwards, we can now account for the heat that was probably always being lost. Remember that as soon as the zinc powder was added and heat started being produced, heat also started to be lost. Although our setup, we've tried to maximize the efficiency of the setup and minimize the heat loss, unfortunately some heat will always be lost. So we will assume that as soon as heat started being produced, heat started being lost, and that the rate of heat loss is constant. And how we can show that with our data is by extrapolating the line backwards in a straight line. We extrapolate it back as far as the point where the second reactant was added. And note that this is where a lot of students often make a mistake, as they'll extrapolate the line all the way back to the y-axis. But remember that no heat was being lost for those first 4 data points because no heat was being produced. There was no heat to lose. So you extrapolate the line backwards as far as the point where the second reactant was added, and this correlates to the maximum temperature that could have been reached if no heat had been lost. A typical question which you can find in paper 1B is regarding the assumptions that you make when you do these calculations. The first assumption, one which we've already discussed, is the fact that the rate of heat loss is constant, and we calculate the maximum theoretical temperature based on that value. Unfortunately, the rate of heat loss being constant isn't strictly always true, as it will depend on the difference of temperature between the two things which are exchanging heat. However, here, there isn't actually that big a difference between the two things that will be transferring heat, so here it's a pretty valid assumption to make. The second assumption that we're going to make, and this is a very major assumption, when we measure the temperature, we're just assuming that all of the heat that's being released by the reaction that's happening is staying in the surroundings, which is the solution. We assume, for example, that the apparatus, so the calorimeter, the thermometer, the stirrer, we assume that they don't absorb any heat. All of the heat stays in the solution. And we also assume that the polystyrene cup is preventing any heat loss to the surroundings. And we know for a fact that that's not true because we can see the temperature decrease after the maximum experimental temperature has been reached. However, it's still a reasonably valid assumption to make because we adapt our calculations for it. The third assumption is that we assume that the specific heat capacity and the mass of the solution, both of them are the same as water. So we assume that the value we use for C, which you'll get in the data booklet, for water is the same as zinc sulfate, which again is not strictly true. And for the mass, we assume that a solution, which is a density of 1.0 grams per centimeters cubed, that's water, we assume that the solution has the same. Again, not strictly true, but the impact that this would have in the calculations is pretty negligible. An example of an exam question in paper 1B, which would be considered medium to difficult level, is shown on the screen. This question is worth 6 marks, so if you want to pause the video and set a timer for 9 minutes, you can rejoin us as we discuss it later. One of the things that makes this question slightly more difficult is the context of the question. So in this question, your second reactant is water, which I think can throw some students off. You're adding copper sulfate to water, which causes a temperature increase, and the whole thing is happening inside a polystyrene cup. They dissolved a particular mass of anhydrous copper sulfate in the water, and the first question asks you to calculate the amount of moles of anhydrous copper sulfate that was added. You would do this using the formula N is equal to mass over molar mass. So the number of moles is mass over molar mass. And the molar mass you can get from the periodic table. The mass is 3.99 because that's given to you in the question. This works out as being 0.0250 moles. Part B asks you to determine what the temperature rise would have been in degrees Celsius if no heat had been lost to the surroundings. We know that the point where the plateau ends at the beginning, that must be when the CuSO4 was added to the water. So you started with a polystyrene cup of water and you added the copper sulfate. This must have been added at around maybe 120 seconds. Then we see a temperature increase and the solution reaches the maximum temperature. And at this point, the rate of heat production is less than the rate of heat loss. At the beginning, in this section, the rate of heat production by the reaction was greater than the rate of heat loss. Here, the rate of heat loss is greater than the rate of heat production because no more heat is being produced. So if we find the intersection of those 2 points, we can identify the maximum temperature that the solution could have reached if no heat was being lost. And the difference between these two temperatures is the temperature rise, because that's the focus of the question. This works out at being approximately 7 degrees. You'll notice how they give a small range, so you really need to be quite careful when you're doing this. Make sure you use a sharp pencil and that you draw your lines as carefully as possible. The range here very narrow for both of them. Part C asks you to calculate the heat change in kilojoules when this mass has been dissolved in the water. So from part B, we know that the temperature rise is 7 degrees Celsius. So my change in temperature is 7 degrees. I know that it was added to 50 centimeters cubed of water, and I know that the density of water is 1 gram per centimeters cubed, which means that if I have 50 centimeters cubed, it would be equivalent to 50 grams. When that's multiplied by the specific heat capacity of the water, which you can simply read from the data booklet, you get a value of around 1463 joules. You're asked to give that in kilojoules, and you'll give it to 2 significant figures because your temperature has 2 significant figures. So 1.5 kilojoules is your answer. In part D, you're asked to determine the value of the delta H in kilojoules per mole. So what we know so far is that the energy that has been released, or the energy that the water has gained, is 1.5 kilojoules. That's because the 0.0250 moles of copper sulfate released it, which means that per mole, what was released was minus 60 kilojoules per mole. Note here that you have to express this as a negative value. Part C asks you to calculate the heat change in kilojoules when this mass has been dissolved in the water. So from part B, we know that the temperature rise is 7 degrees Celsius. So my change in temperature is 7 degrees. I know that it was added to 50 centimeters cubed of water, and I know that the density of water is 1 gram per centimeters cubed, which means that if I have 50 centimeters cubed, it would be equivalent to 50 grams. When that's multiplied by the specific heat capacity of the water, which you can simply read from the data booklet, you get a value of around 1463 joules. You're asked to give that in kilojoules, and you'll give it to two significant figures because your temperature has two significant figures. So 1.5 kilojoules is your answer. In part D, you're asked to determine the value of the delta H in kilojoules per mole. So what we know so far is that the energy that has been released, or the energy that the water has gained, is 1.5 kilojoules. That's because the 0.0250 moles of copper sulfate released it, which means that per mole, what was released was minus 60 kilojoules per mole. Note here that you have to express this as a negative value.